Let's discuss a feed system design of a feed system, which can be feed of anything. Let's say Twitter, Instagram, Facebook, etc. So most of the system we will be discussing, all the components can be used in any of the feed if you are getting asked in a system design interview. So as usual, let's start with the requirement gathering process. So our feed can have text, images, videos. We need to manage out likes and comments on a post. Users can publish posts and view their feed. So majorly we will be focusing on two scenarios. A user can publish a post and they can also view their feed as well. Feed needs to be user specific and computed based on algorithm or some sort of strategy. The feed needs to be user specific. That makes sense, as each user, based on the choices they have made, all the options they have chosen, the people they follow, so their feed should be specific to that. So we need to compute it based on some sort of algorithm or strategy. Scale well up to say 100 million total users. On user feed, show posts by people whom this user follows. So a user will be shown the posts of people whom they follow. These seem more than enough features which can be discussed in the system design interview if asked for to have it for a feed system of anything, Twitter, Instagram, again, anything. So we'll try to majorly discuss in terms of, let's say, Instagram, so that our post can have some sort of picture or a short video clip with the likes, comments, tracking that sort of stuff. Then seeing the multiple flows a user can take of making a post or viewing the feed, and then viewing the likes, comments, counters, and that sort of thing, and how the DB schema will play out, and how the images, video, text of a post will be stored. So all these sort of things. Now let's see back of envelope estimations. As it was mentioned in the requirement gathering that we need to scale up to 100 million total users. So let's assume 50% of people use it actively. So that becomes 50 million. Out of those, let's assume 20% post some content. That becomes 10 million per day. Let's take per user makes 2 posts per day on an average. So that makes it 20 million posts made per day. Then the viewing of feed is done by everyone. So viewing is done by the majority of people and lesser people. That is why we took just 20% people out of everyone makes the posts. So viewing of feed is done by everyone. So let's take that as the overall value as 50 million. So now let's see the QPS, or as queries per second. So let's see the queries per second to be made on posting the content. So as we saw above, 20 million posts per day. So 20 million per day. So QPS is queries per second. So we divide that by per day as 24 hours and then 60 minutes and then 60 seconds. So that becomes 2 into 115. So sort of around 230 posts per second, which is also a decent number. And then the queries per second of viewing the content feed, similar calculations we do with 50 million. So this becomes 50 into million divided by again similar number, 24 into 3600. So that becomes almost 578 feed views per second. So as we can see, overall, and generally also overall for a feed system, generally reads is much higher than the writes. Hence it's a read heavy system. Our availability of the overall system, and especially the two services, which is post content and view feed, needs to be very high, right? Even though consistency can be a bit less on the strong front. So this can be an eventually consistent system. So as per the cap theorem, you can have two strong areas for it, and P has to be there, which is you need to have a partition tolerant system. So you can choose among having a very strong consistency or very high availability. That depends on the use case. So this we can cover in a separate video, or feel free to read about cap theorem. Cap theorem. So you can go ahead and read about that. So we will try to have AP as strong, and then also have an eventually consistent system, and not that strong of a consistency, which is fine for our use case of feed system. We are fine with, let's say, couple of users making a post and us viewing it eventually in some time. We don't want that. We want to see it immediately, right? After all, it's just posts. Now let's continue on back of envelope estimations for the storage part. So for storage, say, let's assume a text takes up 100 KB of space, including all the post text, the description, the comments, the metadata, all that sort of stuff. With image, we can assume just 40% of content has image with it. Let's take an image takes up a storage space of 1 MB. Similarly, for short videos, let's assume out of the overall content, say 5% has short videos in it. Let's assume, so this would be per image. So let's assume the short video takes up 5 MB of storage per video. Okay. So we saw above that 20 million posts were being made per day by our active users. So text storage, let's say for 5 years, will take up 20 million per day. Each text we took is taking up 100 KB of storage space. That was per day. So into 365 into 5 for 5 years, that becomes, so 20 million times 100 GB, this becomes 2000 GB into 365 into 5. So that sort of becomes 3000 TB of storage is needed just for the text alone, for storing the description of a post, comments of a post, metadata along with it, and that sort of stuff. So storage seems much on the higher side with just even the text, dealing with text alone. We haven't even considered image and videos yet, storage of that. Text alone seems quite high. So it's good to use cloud storage like S3 or Google Cloud Storage for storing images and short videos. And that makes much more sense not to store image and videos along with the text, as we saw that text alone took 3000 TB for storing it for say 5 years. So the images and video can be stored on using cloud storage, and the metadata of that, the relative URLs and along with some metadata, that can be stored at our end. So, as I mentioned, and then storing their references in our DBs, right? Makes much more sense. So on a very high level, let's see what these two flows, what we discussed. So we have two segments flow. One is users viewing their content feed. So we need to generate feed of user so it can be shown the posts of people whom he or she follows. Makes sense, as we just discussed. Let's consider this flow to be X and another flow to be Y, which is user posting the content, which would be post would come and we need to store it in our DB. So this is what we can think of at a very high level. So for viewing the feed, we can have the API as using a get method v1/feed with auth with it, right? Auth token needs to come and we would validate at our API gateway or our API server side. And then there, the Y flow, this flow would need a post method call at v1/feed we can consider, which will have auth and also the content payload, which needs to contain all the payload needs to contain all the information that we want to be stored and eventually displayed at the post, and we need to store it in our database. That would include all the text, the description, post related stuff, image, video, etc. As we just discussed above, during our back of envelope estimation for storage, it's not optimal to send the overall image, video, text, and all these sort of things, everything in the payload to our v1/feed post API call and let our servers to handle everything. it would definitely overload our API servers. So what initially can go behind the scenes while invoking our post content API? What we can do, let's try to see it from a UI perspective. Let's say we have this UI. This is our image and video we attached to it, and then we gave all the description and all the text related stuff. It will upload our image or video, whatever we want to go with our post, to our API servers. API servers would reach out to our cloud storage, whichever we are using, S3 or GCP or GCS. It would reach out to the cloud storage and ask the cloud storage to give the API servers a pre-signed URL. Also, pre-signed URL has some expiration time attached to it. So all that upload and all those sort of things need to be done within that expiration time. Else that URL gets expired and our API servers would need to again ask the cloud storage to give another pre-signed URL to which the user can upload some stuff. Then once it receives the pre-signed URL, the API servers would return this pre-signed URL to which the user from the UI would upload the image, video, that sort of stuff. So uploaded via pre-signed URL, and that gets uploaded to the cloud. And then it returns the URL reference plus some metadata in the response, which would eventually go along with our post content API call, which we are making. Then we will make the post v1 feed post content call. Now here, all our text information, our auth and that sort of other things, plus metadata, plus URL reference will be attached, and it would go along with our API call in the payload. This metadata, URL reference, all these sort of things, as we just discussed above, will get from the cloud storage in the response. So whatever we know, let's see if we can draw out a system design, very high level, of posting the content. So let's say user is using mobile or web anything. It makes a post call of v1 slash feed. All that upload to the cloud storage happened, pre-signed URL, getting the URL reference and the metadata, all that sort of stuff has already happened. Now what will happen is this will come with all the payload attached to it. Okay. Call goes via load balancer. It reaches the API servers. Now what API servers need to do is couple of things. One is it will pass it to the post service. Okay. It passes to the post service so that all the payload, text related information, the metadata, the URL references, everything gets stored in our DB to store all the post content and related mappings, right? Then it needs to invoke another service, let's call it feed fan out service. This one, what this needs to do is this fan outs this post which this user is trying to post to all users feeds who follow this user X, right? So this user X made a post, right? Let's say, for example, this is my user X. Okay. So this is making a post, and this user X is being followed by, let's say, A, B, C, and D, right? They all follow this user. Now, as we saw with the requirements and how feed works is this user X makes a post. All the people that follow this user will start getting to see the post in their feed, right? So we need a fan out service for that. This fan outs this post to all user feeds who follow this user X who published this post, right? This makes sense now. And then the third thing is to invoke the notification service to basically again send out notifications to all the users who follow this specific user X that this user X has made some post. So a push notification on their devices so that they can immediately click on that and view it immediately if they are online. This notification service is out of scope of our requirements currently, but I have already done a complete system design video on the notification system, so you can check that out. Now let's see DB schema design. Here the post service will be storing everything related to a post in our database and all the mappings of that with the user who made the post. So let's see that. So we would require, if we try to think from a high level, we would require a post table. This would need a post ID. Let's take it a primary key. This needs to be unique. Then there will be a user ID. Then text like description and that sort of stuff related to that post. Then created at, updated at, timestamp fields, and couple of other fields. Then we need a media table. This post table will be related to the media table. It will have a media ID. Again, that's unique, so we can have a primary key as media ID. Then we'll have a post ID. So for which post we are storing details in our media table. Then the user ID, which made the post. Then the media type. This can be image or video. And then the URL reference, which we got from our cloud storage. Then metadata and couple of tags related to that. So all that sort of stuff and couple of other fields. I would like to mention I'm ignoring the user table as it's quite common to have user ID, username, name, email, contact, when was the user created, last logged in, and couple of other fields. So that's pretty common. Then as in the requirement gathering, we saw that we need to manage out likes and comments eventually made on a specific post. So let's see in our DB schema how that would play out. So for storing likes, we would need a likes table. This can contain a post ID on which the likes are being made, the user ID who made the like. Then combination of this can be treated as a primary key, then created at, when was the like created or made, and couple of other fields. Similarly, we will have a comment table. This will have a comment ID of that specific comment made by the user ID, and then on a specific post, so post ID for that, and all these three fields can combine to form a primary key. Then text, what was the comment made and when was the comment made, so again created at field, and again couple of other fields as well. Let's come to activity feed in some time, why this table would be needed. So let's come to that later when we discuss while building up the news feed, while building up the feed, then this would actually be used, and then we will be able to relate it to more. For storage, it's good to use hybrid storage systems depending upon the use cases. So depending upon our use case, we would require, so post media tables we can use, for example, let's say SQL, RDBMS. But for likes and comments, as these are write heavy, as we would be getting lot of likes from lot of users on a particular post, and similarly for comments as well, so these seems write heavy. So for every like and comment we are getting, it's not good to make the DB call and store it in the SQL and then have all the mappings play out. So for storage, it's good to have a hybrid storage system. Let's see what we can have that. So first, coming to post and media, we need RDBMS, say SQL, to gain all the asset benefits, say SQL, acting as a source of truth for many things. That makes sense. But for likes and comments, as we just discussed, it would require the likes and the comments API calls will have high write throughput. So we need a high write throughput system to handle that. So say Cassandra can play a good role in this. It works upon LSM and SS tables. You can check my video on this. I have already discussed a lot more in detail how Cassandra works, how LSM trees, SS tables, all these sort of things work out, and how they are able to handle a system where the write throughput is quite high. and how they play out while doing the lookups during reads. So all of that is discussed a lot more in detail in this separate video. On a high level, once you have watched the video, you will be able to understand now a couple of things. So for likes, partition key, we can keep post ID so that all likes related to a post goes into the same partition. Similarly, for comments as well, we can keep the partition key as post ID so that all the comments done for the specific post ID will go into the same partition in Cassandra. Now we also need follow table. That is pretty easy to think about. We will have follower ID, we will have followee ID, then created at, when was the follow created, and couple of other fields. Combining the follower ID and followee ID, we can have as primary key. So basically we can extract out which user, which users follow user X, or user X follows what all users, right? So these couple of questions can easily be extracted out from this table. This can also be stored into SQL, so that's fine. Now while pushing post, now while user X is pushing the post, we can synchronously save it to our SQL DB with mappings on user X. So all the post related content, so all the post content, post plus media content, we can directly store synchronously to our SQL DB. And then we can asynchronously fan out to feed of all the users who follow X. As these were the two flows while pushing a post, specific user pushing a post. So the fan out system is good to be done asynchronously, as there will be heavy computations involved. There would be heavy computations involved, plus multiple flows further on that, multiple flows further on the fan out, and synchronously we can save it to our database, all the post, media, and that sort of content related to the specific post the user X made. Okay. So let's see how the fan out system, we can design that and what all things it needs to do. So consider we have this fan out service. What it needs to do is, firstly, so from a very high level, think about that. Let's say, as we earlier also saw, we have these 4 users. Now this definitely will be couple of 100,000 million users. Let's say they follow user X. Let's say user X, let's say user X is a normal person, so it can be couple of 100 or 1,000 followers or so. Or let's say user X can be a celebrity, so that might be like couple of 100,000 or million people following user X. So that can be a normal person or a celebrity. And based on that, fan out would play out. So let's say they all follow user X. So first purpose of fan out service would be, from the DB, from the follow table in our DB, get all people who follow user X. Makes sense, as we need to fill up the feed of all these users who follow user X to populate with this post, so that this post can be shown in their feeds when they try to view their feeds. Second thing that fan out service needs to do is to, let's say, have a ranking service and call that. Now try to think about, let's say, a specific user is following couple of 100 or thousands of users, right? And let's say out of those, let's say 10,000 user, 1,000 users made the post, considering 10% of it. But when the user A, opens up their feed, we can't show them and populate their feed with all the posts made by these 1,000 people. This is where ranking service comes into play. We need to sort of have some sort of strategy or algorithm play out so that it can organize the posts and sort of select, let's say, top n posts, which can be, let's say, top 20, top 50, or top 100 posts out of all the posts. So we can have give a scoring to the each post. Now that can be based on user has blocked or mute a specific person, based on the affinity of the user, how close certain users are to this user, then the timestamp of the post, when was the post went, when was the post actually made. So all these sort of things can be combined to get a score, and based on that we can organize which has a better score will be picked up earlier of our top n posts, where n can be, let's say, 50. So based on this score it would be picked up. So once that is done, we have now picked all the people whom whom whose all feeds we need to populate. Okay, then we are calling this ranking service to find the scoring of this certain post for all these users who follow user X, which would eventually have scoring for all these users based on their um, strategies, which can be block, mute, affinity, timestamp, and that sort of thing. And then the third thing would be to send or publish now the post created event. Now this event would go to a message queue, and then we will have our fan out workers which would consume these messages and then go and populate the posts on all the friends or people that followed user X. So feed cache of all of those. Make sense? Let's try to discuss this overall process a little bit more in detail. So for someone with say 1k, 5k, 10k, etc. followers, this strategy works of fanning out on right. So this strategy that we discussed above, this is called as fan out on right, which is as soon as the post by user X was triggered, the post call was triggered, it got stored in the DB, and in the second asynchronous flow, the fan out service actually went, fetched all the information, all the scoring and that sort of stuff from ranking service, and then triggered the post created event, and fan out workers would start picking up the event and actually populating the feed cache of all the people who follow X. So this is fine, as I mentioned, if the followers are, let's say, 1000, 5000, 10,000, something like that. Let's say this many people follow user X. So this is fine. We need to populate feed cache of all these users. This is fanning out on right. But for someone who is sort of a celebrity, as we discussed over here as well, the user X can be normal person or a celebrity. That celebrity person won't have 1000, 2000, 5000 followers. It would have, let's say, 100k, 500k, million, 5 million, etc. people following them. So once this celebrity makes the post, actually fanning out on right becomes a very heavy computation process to be done. So fanning out the post details might be too much of an overkill, and that makes sense. Fanning out and populating the feed cache, firstly getting out all the followers, then getting out all their rankings and that sort of stuff, seeing their user affinity, their block mute, all that sort of things, and then populating the feed cache of, let's say, 500k or 1 million followers. That becomes like an overkill process. Considered not every one of that 1 million followers immediately need that post in their feed. Now this becomes sort of a hotkey problem if we try to fan out on write itself. This is where a separate flow fanning out on read works much better. Also along with this, we need to store the post details, references majorly to Cassandra as well, depending upon our fan out strategy. This will hold all the posts of each user's feed, content posted by their followers. Unlike Redis, where it's inefficient to hold all of this in memory, there we can keep post references of a feed of a certain user to say top 50 or 100, etc. Right? So this is the feed cache, as we are storing it in Redis, so that's in memory. So this is where we can store, let's say, top n posts for a certain user. Top n posts can be stored in Redis cache, that's in memory, rather than storing all the posts that are being made by the people this certain person follows. So this is where, as we left out that certain table, activity feed table, this also needs to go into Cassandra, as that is also quite a lot of information. And then we want, then there is a lot of writes coming in. All the posts that the user, say a user A is following all the people and they all making the posts, so user A's feed being built up. So all that sort of information, it's good if it goes into Cassandra rather than SQL. And then lookups is also quite fast, and then we can also have highly efficient range queries. That all you can again visit my and check out my how LSM trees and SS tables work and play out together to do the range queries, lookups using Bloom filters, and able to scale well with a high write able to scale well with a high write throughput system. Activity feed needs to store, say, user ID and the post ID. So the posts and the user ID, so all these things would be references to the actual post table and media table. We don't need to fill all the information related to a post. References are more than enough. Then the score, then author ID, and then timestamp fields. And then this user ID and post ID can become the primary key, right? So this much information seems more than enough. Once all of this storage is done, making a post, storing its post details, its references, populating the feed cache of the users who follow this certain user which made the post. Once all of this is done, then let's see a high level design of viewing the feed. Now let's say we have a user Y who logged in and wants to view the feed. It will make a get v1 slash feed call once it is authenticated and all that sort of stuff is done. Call would go via load balancer. Then it hits the, let's say we have a feed service. It would do again couple of things. This feed service would do would bring data from multiple sources, plus do some computations on it. Why multiple sources? Because we can't just rely on the Redis feed cache data, because it can be the posts. Firstly it's just the top n posts, and it will be the posts made by the people whom this user Y follows, but they went into the flow of fanning out on write. So Redis, to extract all the mappings of post ID and user ID. So in Redis, let's say the data was stored again as references, post ID and user ID, and not the overall post and media details. Then it would go and call Cassandra to extract out posts which came via fan out on read. Let's say this user Y follows couple of people who have very high followings, let's say 500k million, or are celebrities, tagged as celebrities. So that didn't went into the, as we earlier discussed, fan out on write flow. They went for fanning out on read flow. That is, the data will be pulled while this user X is trying to give it a read to their feed. So we need to extract out posts which went via fanning out on read, made by the celebrities, which didn't fan out while posting content. So didn't play out the flow of fan out on write. Then once it gets all the post IDs and couple of other details, it would hit the database to bring out It will hit the database to bring out all the post details, media details, and all that sort of stuff. And also, Redis cache is fine, but to actually go, okay, to extract out actual post content and media. So that's also good enough. Let's try to discuss what we just designed a little bit more in detail. So feed service fetches follower list from DB and filters out the celebrities from that. As Cassandra had everything, all the information, because we can't just rely on Redis, which is in memory cache. So we need to get all the follower list from DB and filter out celebrities. This can be done by storing a tag alongside user ID in DB. So all the users inside the user table, this can be updated of having a tag as being a celebrity or not. So that sort of tag, and based on that, filtering can play out. So based on the IDs, it fetches posts from Cassandra activity feed table, which we just discussed above, which has partition on user ID. So we can get all the posts made by this certain celebrity, right? Makes sense. This further does lookup on SS tables and can extract out right amount of posts, right amount of posts from that, say, based on timestamp, right? So we got all the IDs of the celebrities from the follow table and the user table from our DB. Then we hit Cassandra's activity feed table to get all the posts made by these celebrities, right amount of posts, and Cassandra would look up on the SS tables. Again, all of this in depth, how lookup works and that sort of stuff, although we'll discuss a little bit in detail below, but best to check out that video. Merges post in feed service, which it got from Redis feed cache, which was pre-computed with fan out on write and Cassandra fan out on read. So now, once we collect all the posts, our feed service will merge these posts together, then extract out actual post content from DB, posts and our media table, and builds out the feed. So it would merge the posts which it got from Redis and Cassandra, then play out some ordering based on scoring and couple of other strategies. It will get the top n posts. So of the top n posts, say 50 or 100, and we can also involve pagination here so that every 10 posts get fetched once or per page. So extracts out, then it, considering as we just discussed, it only has references stored both in Cassandra and Redis. So it would actually fetch out the post content from our SQL database, all the post media references. Then for the media, it would get the URL references, and then it would actually hit the cloud storage to bring out and download the video or the image. And then it builds out the overall feed for that n number of posts. Now let's see likes and comments feature. Okay, let's see our likes and comments feature. Likes and comments are write heavy features, as we discussed in the very beginning. As per post, we can have thousands, 100,000 likes, and similarly hundreds and thousands of comments, right? So we can have very high number of likes and comments per post. So rather than using SQL here, Cassandra DB seems a good choice for this, as that scales very well with very high write throughputs. Again, check the video on LSM and SS tables, how it all handles very high write throughputs, then all that sort of lookups using Bloom filters and range queries and that sort of stuff at a good scale. Our likes and comments can have partition on post ID, so that for a specific post, all the likes and comments will be present in the same partition, so that, as I mentioned here as well, so that each partition consists of data, likes and comments related to a specific post ID together, and they can be further stored based on their descending order of time. Makes sense. So that the likes and comments made by people recently appears at the top. For comments that can directly be written to Cassandra. So for comments, they can directly be written to Cassandra. And this makes sense. As a partition key is post ID, so all comments of a post stay together. This makes it good for this sort of query. Load comments of a specific post, which is the general use case. Let's see for comments what would happen behind the scenes, although I have already covered in my video of LSM and SS tables, a little bit depth in what Cassandra does behind the scenes, but let's see a little bit here as well to understand more on how comments would go and be stored, how lookup, range queries, and all that sort of stuff would play out behind the scenes with Cassandra. So Cassandra has a mem table and an append only log. So our comment behind the scene would go to mem table and the append only log. It will store comments of a post, and these are in memory. So mem table is in memory. They then get flushed to SS tables. SS table. This can have comments data from multiple partitions. Now, as we just discussed, each partition is based on the post ID so that all the comments related to a post ID stays together. But when they get flushed to SS table can have comments data from multiple partitions, and these are immutable. As the SS tables fill up, it starts flushing data now to new SS tables and further. Now, during lookup, it scans all the SS tables and checks with, say, using Bloom filters, which SS tables might, as the Bloom filter has that the comment related to this certain post ID is not present or might be present. So with not, we are good enough. We don't have to scan the index of our SS table. And with might be, we definitely have to scan that. But still, we have lowered the overall scanning of our SS tables. So have it or not eventually, have comments data related to a post ID. Then it gets data from mem table plus all valid SS tables, which got the might with using Bloom filter and got the comments from that, from those SS tables. It merges them to get top n comments, right? So from a very high level, let's see, this is our mem table. So data, as we just discussed, is organized based on the partition key. Partition key, we took it as a post ID. So post ID 1 has all the ordered comments of post ID 1, post ID 2 has all the ordered comments of post ID 3, post ID 3, sorry, post ID 2, post ID 3 has all the ordered comments of post ID 3, and so on. So that each partition key, which is a post ID, has all the comments related to that specific post ID. Make sense? Then let's discuss a little bit on the SS table. So data from multiple partition key, hence comments related to a specific post ID, can be present in any of the SS tables depending upon when they arrived on mem table and got flushed to the SS table. Makes sense, because SS table can have data from multiple partitions. So lot of our SS tables can have the comments stored along with other partitions and their comments of their posts. So depending upon when these comments arrived, it could be present and flushing happened to SS table. It could be present on multiple SS tables, but still Bloom filter helps during lookup and we don't have to scan all the SS tables. Now let's see for likes. For likes, we can store them directly in Cassandra, similar to what we did now for comments earlier, but that doesn't scale very well. And that makes sense. Let's say a post has maybe 100 comments, 1000 comments, but definitely likes, if a post having 100 or 1000 comments, likes would definitely be 100,000, 200, 500,000 or so for such a post. So it won't scale well if we directly hit our Cassandra and store the likes. And then we also need some sort of counting mechanism to be displayed on the UI, how many people have liked. And then once we go into that, we need what all users liked it. So we need the counter. So we need the counter of how many users liked, and then going inside, we want to know who all liked it, like who are those users. So likes need a system to handle high burst write QPS, because very large number of users can like a specific post. If that person is quite popular, in a very short span of time they can like it, so it will have a very high burst write queries per second. And then we need a system which handles very quick counter updations, because on the UI counters needs to be displayed very quickly. So for this use case as well, we can think of splitting system into a hot and cold path. So for hot we can take up Redis, and for cold we can take up Cassandra. We will have users tapping on like of a specific post. With Redis, we will increment the counters of that post ID. So we can store key value pairs. We'll see just down below. And for this specific post ID, which can become a part of Redis key to have sort of a uniqueness, we can maintain the counters for that. Alongside all of this, we can have an aggregator which accumulates these likes over a certain time window and then triggers a like event to Cassandra. Now we can't just keep all these likes in memory in Redis. We need to eventually store them to Cassandra, which all users made the likes and the like counters. So again, emitting all events per like will put and overload our system. That would also be an overkill for very high burst write QPS as we will have for likes. So what we can do is we can have an aggregator that runs on a certain time window, let's say a minute or so. It aggregates all those likes and user IDs which made the likes and its counters, and then triggers a combined like event to Cassandra. Let's discuss a little bit more in detail. To store like counter in Redis, we can have a key. We can think of a key as post colon post ID. This is dynamic colon like count. So this makes it unique as it involves a unique post ID. As key, this would be a key, and counter as value for which INCR operations can be used with Redis. To store which user made the like, as we also need that information. So our key can be post colon post ID colon likes. So again, this is unique. So keys would be unique for all the users which are making that post. And then in this key, we can have values as user ID which made the likes. And then we can use it as a sorted sets or something like that, or a list in Redis with list of all these user IDs on this key. List of all user IDs which made the like on this specific post ID. Okay? All this gets eventually then stored in Cassandra. So Cassandra, we can think of having a table as post likes, which will have post ID and user ID. This can be treated as a primary key to have uniqueness. And then we will have the like at, and then we can have a separate count table as well to store the counters, and or we can fetch it from here or have the field here as well. That's up to us. That is fine. Now on a high level, let's see how things would play out from a design perspective, what we all just discussed in case of likes. So let's say this is our UI. It will have a post, and below that it will have a like button with a thumbs up, right? So let's say a user came and clicked on it. Let's say user A came and clicked on it. It will trigger a v1/like API with post ID, user ID, post ID of which post the like button is clicked, and user ID of the user who clicked this like button. It would hit our API servers. and then it would update our Redis keys with the specific values, updates Redis like counter and who made the like, both the keys. Once Redis is updated, we can send OK 200 to user that our system has received their like, right? And our aggregator system can work behind the scene to aggregate all these likes and counters from the Redis and then eventually send an event of storing all this information to Cassandra. We can have an accumulator, think of as a cron job. This runs every n time window, say a minute or so. This accumulates what is there in these Redis keys and then emits an event per Redis key to our message queue. So this is our Redis cache. Every n time, say a minute or so, this accumulator accumulates all the information per Redis keys, both counters and of the user IDs who made likes on that specific post ID. Then it emits an event. Then it basically first builds the event. Now, building of the event, it will have, we can think of as a post ID of which specific post it accumulated the counter value and the list of user IDs who made the likes. Say a likes of all the user IDs, list of that, and when were the likes made, then a like count on this specific post ID. So the information info about each post ID, it would build the event and then emit this event to our message queue. From this message queue, we can consider Kafka. We have our workers consuming from that topic and pushes all data to our Cassandra. Let's say we have this, it emit the event, it built the event and emitted it, let's say of like post event or something. So we have our workers which consume from that specific topic, and it would push all of that data to Cassandra. So again, repeating the same thing, like the like happened from the UI. Let's say a user A made the like and couple of other users, A plus others. V1 like API gets triggered. API servers would quickly store that information, update that in Redis keys using, let's say, zadd and incur for updating quickly the counters, and zadd to quickly add the user ID and like that of that specific post ID key, and it returns back with 200 OK that we have received all the information, all well and good. Then behind the scene accumulator is accumulating the information on these specific Redis keys every n time window, say 1 minute or so, and then it emits event to our message queue where our workers are also working to consume these events from the message queue, these message payloads, and then dumping out the data, storing them in Cassandra DB.